Right now, more than 15 billion miles from Earth, a tiny spacecraft is drifting alone in total darkness. And we're still talking to it. How is that even possible? Its signal is weaker than a whisper, yet it crosses the stars. This is Voyager 1, humanity's last voice in the cosmos. But time is running out. Launched in 1977, Voyager 1 was never meant to survive this long. Its mission was simple: explore Jupiter and Saturn, take photos, collect data, then drift silently into the unknown. But against all odds, it's still alive, still sending signals, still listening. As of now, it is the farthest human-made object from Earth, over 15 billion miles away. That's more than 160 times the distance between Earth and the Sun. And yet, NASA still sends it commands and receives data in return. But how do we maintain contact with something so impossibly far away? How can a 22-watt signal, barely enough to power a light bulb, cross the emptiness of space and reach us? And more importantly, how much longer can we keep this connection alive? Today, we'll follow Voyager 1's full journey from its historic launch to the edge of interstellar space, through its most astonishing discoveries, its struggles to survive, and the ticking clock that threatens to end its voice forever. This is the story of Voyager 1, the spacecraft that refuses to go silent. It was the summer of 1977. Humanity was about to attempt something unprecedented, launching 2 spacecraft, not just to explore our neighboring planets, but to fling them into the unknown, possibly forever. On August 20th, Voyager 2 was launched, and just 16 days later, Voyager 1 followed. The names are misleading. Voyager 1 launched second, but it was on a faster trajectory, designed to overtake its twin and reach Jupiter and Saturn first. But what made this mission truly extraordinary wasn't just the ambition, it was the timing. In a stroke of cosmic luck, the planets Jupiter, Saturn, Uranus, and Neptune were aligning in a rare gravitational configuration, something that happens only once every 176 years. NASA saw the opportunity of a lifetime. By carefully timing the trajectory, Voyager could use the gravity of each planet as a slingshot, accelerating faster and faster through the outer solar system without needing massive amounts of fuel. This maneuver, called gravity assist, turned a 5-year mission into a chance at immortality. At the heart of each spacecraft was a 1970s brain, 8-track tape recorders, 68 kilobytes of memory, and computers less powerful than the ones inside a modern digital watch. And yet, they were designed with durability in mind, reinforced with layers of shielding and redundancy. Each Voyager carried a suite of instruments to measure magnetic fields, particles, radiation, and, of course, cameras to capture the sights no human had ever seen. But Voyager was more than just a scientific tool. It was a message to the universe. Each spacecraft carried a golden record, a copper disc coated in gold, containing greetings in 55 languages, music from Earth, the sound of a heartbeat, the laughter of a child, and images of life on our planet. It was humanity's introduction to the cosmos, just in case someone or something found it one day. Still, back on Earth, expectations were realistic. The mission was expected to last only 5 years, maybe 10 if they were lucky. No one imagined that nearly 50 years later, Voyager 1 would still be active, still transmitting data, still pushing farther into the unknown than anything we've ever made. Voyager wasn't built to last this long, and yet, against every expectation, it did. And what it found in its first encounters would change how we see the solar system forever. As Voyager 1 raced toward the outer planets, it became clear this wasn't just a mission of observation. It was a mission of revelation. In March 1979, Voyager 1 reached Jupiter, the largest planet in our solar system, and almost immediately it began transmitting images that defied everything we thought we knew. What had once been a blurry colored ball seen through telescopes was now a swirling, living giant. We saw the great red spot in motion, spinning like a cosmic hurricane larger than Earth. And we watched as white storms the size of continents danced around it in real time. But the real shock came from Jupiter's moon, Io. Voyager captured images that left scientists speechless. Giant volcanic eruptions, spewing sulfurous material hundreds of kilometers into space. Io was geologically active, violently alive in a place we thought was frozen and dead. This was the first time in human history we had witnessed volcanic activity beyond Earth. Why was Io so alive? Because it's trapped in an intense gravitational tug-of-war with Jupiter and its other moons. This constant squeezing heats Io from the inside, creating one of the most volcanically active bodies in the solar system. Voyager 1 also made another quiet but profound discovery: Jupiter's rings. Until then, we believed Saturn was the only planet with a ring system. But there they were, faint, dusty, and barely visible, encircling the gas giant like a ghost. The universe, it seemed, had more symmetry than we thought. And then, Voyager set its course for Saturn. By November 1980, it arrived at the second stop on its grand tour. Saturn had always been the jewel of the solar system, a planet of impossible elegance. But Voyager revealed its rings in staggering detail. Not just a few bands, but thousands, each with its own structure, gaps, and rhythm. It discovered that Saturn's rings aren't solid, but made of billions of particles, from tiny grains of ice to house-sized chunks, held in place by gravity and motion. Among the most fascinating were the shepherd moons, tiny satellites like Prometheus and Pandora, whose gravity shapes the edges of the rings, maintaining their structure like cosmic caretakers. They were invisible to us before. Now they were unmistakable. But Saturn wasn't done surprising us. One of its moons, Titan, emerged as a world of deep intrigue. Voyager detected a dense, layered atmosphere, thicker even than Earth's, composed mostly of nitrogen with traces of methane and organic molecules. It was too hazy to see the surface, but what Voyager sensed was enough to spark a global scientific obsession. Here was a moon with real weather, a place where methane might rain from the sky, forming rivers and lakes in sub-zero temperatures. Titan was no ordinary satellite. It was a world with the right ingredients for prebiotic chemistry and possibly even the precursors to life. All of this from a spacecraft with 68 kilobytes of memory. Voyager 1, in just 2 planetary encounters, had rewritten entire chapters of science. It had revealed that the outer solar system was not just a quiet, frozen graveyard, but a dynamic frontier filled with fire, storms, and strange atmospheres. But the tour, as glorious as it was, had to end. Voyager 1's path pulled it away from the plane of the solar system, upward and outward, never to visit Uranus or Neptune. That mission fell to Voyager 2. Voyager 1's cameras were shut down shortly after, not because it was broken, but to save power for something even greater. It had one last destination, one no spacecraft had ever reached: the edge of the sun's realm. And what waited there was more profound than anyone expected. After completing its tour of the outer giants, Voyager 1 didn't slow down. It couldn't. The gravitational boosts it had received from Jupiter and Saturn had accelerated it to escape velocity, fast enough to leave the solar system entirely. But what exactly does leaving the solar system mean? It turns out that's a more complicated question than you might think. Most people imagine the solar system ends where the planets do. But in reality, the sun's influence stretches far beyond Neptune. It radiates an invisible force field of particles, magnetism, and energy, a vast bubble called the heliosphere. And for decades, scientists wondered, where does that bubble end? Voyager 1 was about to find out. As the spacecraft drifted farther from the sun, its instruments began to detect subtle changes. In 2012, more than 35 years after launch, Voyager crossed a mysterious boundary known as the heliopause, the outer edge of the heliosphere. Inside the heliosphere, space is filled with solar wind, a stream of charged particles constantly flowing from the sun in all directions. But beyond the heliopause, that flow stops. The particles no longer come from the sun. They come from interstellar space, from stars and events far outside our solar system. Voyager's sensors recorded a sudden drop in solar particles and a sharp rise in cosmic rays from deep space. That was the signal. Voyager 1 had officially entered interstellar space, the first human-made object to ever do so. Think about that for a moment. Every other spacecraft we've ever built, every rover on Mars, every satellite in orbit, every lander on the moon, they all operate within the protective bubble of our sun. Voyager 1 is the only one beyond that protection. It's in the raw, untouched space between the stars. And out there, it's alone. No planets, no moons, no sunlight strong enough to warm it. Just a vast black sea stretching for light years in all directions. But even this is just the beginning. Beyond the heliopause lies a region called the Oort cloud, a theoretical sphere of icy debris that surrounds the solar system like a giant shell. It's believed to be the birthplace of long-period comets, and it marks the true edge of the sun's gravitational influence. Voyager 1 is heading straight for it, but it won't get there anytime soon. It will take 300 years just to enter the Oort cloud, and another 30,000 years to pass through it completely. That's longer than human civilization has existed, longer than we've been writing, farming, or building cities. And Voyager won't be sending us data by then. Its power supply will die. Its instruments will go silent. Its antenna will fall out of alignment. But the spacecraft itself will continue, a silent traveler coasting through the emptiness, perhaps for millions of years. It won't reach another star for at least 40,000 years, but it will keep going, unchanged, unpowered, and untouched. It has already passed the threshold no other probe has reached. It has entered a realm we once thought unreachable. And still, somehow, we hear its voice, a voice carried not by magic, but by science, engineering, and a belief that it's worth sending something beyond ourselves. What comes next? A challenge even more difficult than distance itself, staying in contact across the stars. Voyager 1 is now more than 15 billion miles from Earth. That so far, it takes light, traveling at 300,000 kilometers per second, 22.5 hours just to reach it, and another 22.5 hours for its response to come back. Nearly 2 full days between command and confirmation. But here's the real question. How is this even possible? How do we talk to something so far away that its signal should have faded into nothing decades ago? How do we hear a whisper from the edge of the void? The answer lies in a remarkable feat of engineering, one that most people have never heard of: the Deep Space Network. Voyager 1 transmits using a dish antenna that's only 3.7 meters wide, just over 12 feet. And it sends out signals using only 22 watts of power. That's about the same as a refrigerator light bulb. When that signal leaves Voyager, it starts to spread. It travels across the solar system, through interplanetary dust, past the orbit of Neptune, through the edge of the heliosphere, and into the deep interstellar medium. By the time it reaches Earth, it's weaker than a trillionth of a watt, less energy than it takes to trigger a single neuron in your brain. It's the faintest signal we've ever managed to detect reliably. And yet, we do. Because here on Earth, we've built something incredible. NASA's Deep Space Network is made up of 3 massive complexes located in California, Spain, and Australia. Each one is precisely placed so that as the Earth spins, at least one of them is always in line with Voyager's trajectory. These facilities don't use normal antennas. They use giant 70-meter dishes, some of the largest ever constructed. They're so sensitive, they can detect signals thousands of times fainter than the background static of the universe itself. But even with these instruments, it's not easy. To stay locked onto Voyager, the dishes must track its position with extreme precision. Remember, a deviation of just a fraction of a degree at that distance means missing the target by millions of kilometers. That's why the spacecraft's attitude control system, the thrusters and gyroscopes that keep it pointed, is so critical. If Voyager ever drifts too far off course, its tiny signal could be lost forever. On top of that, Voyager's communication isn't constant. NASA schedules windows of time where the Deep Space Network can focus its attention on the spacecraft. During those moments, the antennas send commands, receive science data, and gather basic health reports like battery voltage, temperature, and orientation. And what does Voyager send back? Surprisingly, still quite a bit. Although most of its instruments have been turned off to conserve power, a few key sensors are still running, collecting data on cosmic rays, magnetic fields, and interstellar particles. Voyager is the only probe we have in that environment. Every byte it sends home is a scientific treasure, but let's be clear, this isn't broadband. The data rate is agonizingly slow. About 160 bits per second. That's slower than a 1980s dial-up modem. Sending a single image today would take days. But that's not the point. The data Voyager sends is incredibly valuable because it's data we can't get from anywhere else. There's also another hidden marvel at play. Voyager 1's communication software. It's been patched and reprogrammed multiple times from Earth, despite the fact that it was written for computers older than almost any in operation today. Think about that. Engineers on Earth are still writing code for a spacecraft that launched before the first home computers existed. Of course, it's not just about software or antennas. It's about patience. It's about timing. It's about resilience. Every message we send takes nearly a full day to arrive. Every reply is a test of endurance. We are holding a conversation across time, the longest distance dialogue in the history of our species. And what's even more remarkable is this: Voyager 1 is still listening. That in itself is a miracle of engineering. Every time we send a command, there's a chance it might be the last. The antenna could drift. A glitch could occur. A cosmic ray could flip a bit and crash a system. But somehow, it keeps working. Decade after decade, distance after distance. We're not just talking to a machine. We're maintaining a lifeline to the most distant human object ever created. A lifeline that depends on fragile components, ancient circuits, and a signal so faint it borders on impossible. And yet, Voyager continues to answer. It continues to speak, however softly, from the farthest frontier we've ever reached. But the question is, how much longer can it keep doing that? Keeping Voyager 1 alive isn't just about antennas or trajectories. It's about power, real physical energy. Out there, in the icy blackness between the stars, there is no sunlight strong enough to charge a solar panel. It's cold, it's dark, it's empty. So how does Voyager stay alive? The answer goes back to one of the most remarkable decisions made in the 1970s. Voyager 1 is powered by plutonium. Specifically, it uses a system called a radioisotope thermoelectric generator, or RTG. Inside each RTG, there are blocks of plutonium-238, an unstable isotope that naturally releases heat as it decays. That heat is then converted into electricity by thermocouples, with no moving parts, no engines, and no sunlight required. At launch, Voyager's RTGs produced about 470 watts of electrical power, roughly the same as a small microwave oven. It was more than enough to run all the spacecraft's systems: instruments, heaters, transmitters, computers. But plutonium-238 has a half-life of 87.7 years, and the decay is constant. That means every year, Voyager's power supply gets a little weaker. Today, nearly 5 decades later, it produces less than 200 watts. Not enough to run everything. So NASA has been forced to make hard choices. Over the years, systems have been shut down one by one. The cameras were turned off in 1990, just after Voyager took its final image, the now iconic pale blue dot photo showing Earth as a tiny speck suspended in a beam of sunlight. Since then, no more pictures, only sensors, only data, only silence. The heaters for some instruments were turned off next. Temperatures inside the spacecraft have dropped to levels that would destroy most electronics on Earth. But Voyager was overbuilt, insulated, shielded, prepared for the unimaginable, and somehow it kept working. Today, just a few science instruments remain active, measuring things like cosmic rays, plasma waves, and magnetic fields. And even those may not last much longer. The engineers at NASA's Jet Propulsion Laboratory, some of whom weren't even born when Voyager launched, now monitor the spacecraft like doctors tending to an elderly patient. Every watt is accounted for, every signal is double-checked, every decision is carefully debated. Should they turn off another instrument? Should they reduce transmission frequency? Should they change how often the spacecraft updates its orientation? Each answer costs time, power, or capability, but the real enemy isn't just power loss, it's aging. Voyager's components were built with 1970s technology. Its circuits are decades old. Some backup systems have failed. Redundancies are running out. And yet, with each year, the spacecraft continues to function beyond any realistic expectation. In 2020, NASA devised a clever workaround to reroute power between systems using unused hardware pathways. In 2023, they began experimenting with altering the timing of internal systems to reduce demand on critical components. These aren't software patches. They're creative engineering miracles done remotely, with a 22.5-hour delay between command and confirmation. There is no turn it off and on again. Every move is irreversible. Every error could be fatal. And yet, they persist. Eventually, sometime around 2026, engineers expect that only one science instrument will remain online. After that, perhaps a few more years of basic telemetry, just enough to tell us Voyager is still alive. By 2030, it may fall silent. And yet, even after it stops talking, Voyager 1 won't be dead. It will still be moving, still drifting, still powered, faintly, by the last radioactive decay deep inside its heart. A ghost ship coasting through the void, no longer speaking, but still listening. And in that silence, there's something poetic. Voyager isn't just a machine, it's a symbol of endurance, of how far human ingenuity can reach. of how long a single spark of curiosity can stay alight, even as the universe grows colder. But while there's still power, while there's still light in the core, there's still a voice. And NASA intends to listen until the very last whisper. When you send a machine into space for 5 years, you build for 5 years. You prepare for known risks. You reinforce what you can. But you don't prepare for 50. No one could have predicted that Voyager 1 would still be flying half a century later, and certainly no one expected it to still be talking. But surviving that long comes with a cost. Voyager's systems have endured cosmic radiation, micrometeoroid impacts, and the slow degradation of electronics aging in a vacuum. And yet, the biggest threats aren't dramatic explosions or collisions. They're far quieter, subtle, invisible. Bit flips, voltage drops, frozen valves, corrupted memory banks. In 2023, Voyager 2 suffered a near-catastrophic event. Its high-gain antenna, a dish that must remain precisely aligned with Earth, drifted off by just 2 degrees. That tiny error was enough to cut off communication entirely. Silence. Total blackout. For weeks, NASA heard nothing. Engineers feared the worst, but Voyager had been programmed decades ago to realign itself periodically, just in case something like this happened. Sure enough, on schedule, the spacecraft slowly adjusted its attitude and regained contact. Against all odds, it found its voice again. Voyager 1 hasn't been immune to problems either. In late 2023, it began returning garbled data. For months, engineers were baffled. The systems were online, the transmitter was working, but the information being sent made no sense, like a scrambled radio signal with no pattern. The team at NASA eventually diagnosed the issue. Voyager was trying to communicate through a memory bank that no longer functioned. Something in its internal systems had shifted, possibly due to a cosmic ray strike or aging circuitry. The spacecraft was alive, but using the wrong pathway. After weeks of analysis, the engineers crafted a new command, redirecting the data flow to a working system. They uploaded it, waited 22.5 hours, and then came the reply. Clean. Clear. It worked. A 46-year-old spacecraft running ancient hardware had just been successfully rerouted in deep interstellar space. These aren't just repairs. They're acts of deep space surgery performed from across the solar system with delays of almost a full day. Every command must be perfect. Every solution must be elegant, because there is no margin for error. There is no second chance. Another challenge: the thrusters. Voyager uses tiny bursts of nitrogen gas to adjust its orientation, keeping the antenna locked on Earth. These aren't big rocket engines. They're about the size of a pen cap, and they've been firing in microsecond pulses since the 1970s. Over time, the plumbing inside those thrusters has started to clog as residue from decades of fuel combustion builds up. NASA's response: reprogram the flight software to fire the thrusters for slightly longer but less often. That small adjustment reduces wear and may extend thruster life by up to 5 years, a priceless gain at this stage of the mission. There's a quiet brilliance in this work. These aren't flashy breakthroughs. They're not headlines. They're gritty, patient acts of engineering rooted in obsession, respect, and a deep love for a machine that's lasted far beyond its time. Voyager 1 is now supported by a team of engineers and scientists, some in their 20s, some in their 70s. For many, this spacecraft is older than their careers. For others, it was built before they were even born. And yet, they all share one thing: the drive to keep it alive, to nurse it forward, to squeeze out every last packet of data from the edge of the cosmos, because they know what it means to lose contact, to hear nothing, to send a command and receive only silence. That day will come, but not yet. As long as Voyager 1 is still out there, still ticking, still pointing its antenna at a pale blue dot nearly 15 billion miles behind it, NASA will be listening. Voyager 1 is still alive, still talking, still flying, but not even the most remarkable machine can outrun time. Its power source, those nuclear generators powered by decaying plutonium, is growing weaker with every passing day. When Voyager launched, it had enough energy to run everything: its instruments, its heaters, its transmitters, its stabilizers. But now, nearly 50 years later, it's running on less than half the power it once had. And that means hard decisions. NASA's team has already shut down non-essential systems. The cameras were the first to go, more than 3 decades ago. Then came the heaters for individual instruments. Then entire scientific packages, one after the other, slowly went dark. Today, only a handful of instruments remain active, each one drawing just a trickle of power, each one precious. Soon, even those will need to be turned off. According to current projections, by 2026, Voyager may only have enough energy left to run one final instrument. And sometime after that, perhaps as late as 2030, even the ability to transmit a signal will disappear. At that point, Voyager will go silent, not because it failed, but because it did everything it could. After more than 5 decades of continuous flight, of transmitting across the stars, of surviving radiation, isolation, and entropy, Voyager will no longer be able to call home, and we will no longer be able to listen. But its journey won't end there. Voyager 1 will keep drifting. It will pass stars. It will pass the Oort cloud, slowly, silently, on a timeline so vast it's difficult to comprehend. It won't reach another star for 40,000 years. It won't leave the sun's gravitational influence for tens of thousands more. And yet, it will carry with it the golden record, that metal disc encoded with sounds, greetings, music, and images from Earth. A kind of interstellar message in a bottle. A time capsule from the late 20th century, floating forever in the void. There's a real possibility that no one will ever find it. That Voyager will wander alone for millions of years, unseen, unheard, unremembered. But that's not the point. Voyager's mission has never been just about being found. It's about leaving something behind, about stretching the limits of what we can reach, about proving that we, as a species, are capable of sending our curiosity beyond the edge of everything we know. Right now, we still have time. We can still send commands. We can still receive data. The line is still open, but we're in the final chapter. The clock is ticking. And when that final signal is sent, when that final whisper reaches us from the black, it will mark the end of one of humanity's greatest achievements. But even after the silence begins, Voyager will still be out there. Voyager 1 was never supposed to become a legend. It was built quickly, on a tight budget, with 1970s technology that, by today's standards, seems almost laughable. Its memory is just 68 kilobytes. That's less than the size of a single photo on your phone. Its processing power is slower than a pocket calculator. Its communication speed is a fraction of a dial-up modem. And yet, this machine, cobbled together with wires, foil, and silicon, has become the most distant object ever created by humans. Its discoveries changed the way we see our solar system. It revealed volcanic moons, hidden rings, active atmospheres, and mysterious magnetic fields. It showed us a universe far more dynamic, violent, and alive than we had imagined. But its greatest achievement wasn't just what it found. It was how long it lasted. Voyager has endured the impossible. Extreme temperatures, cosmic radiation, failing systems, and the slow decay of time itself. It has survived everything the universe could throw at it, and still, it flies. But beyond the science and the milestones, Voyager has come to represent something deeper, something profoundly human. It represents our need to explore, our hunger to reach beyond the visible, our desire to leave a mark in the silence of the cosmos. It's not just a spacecraft anymore, it's a symbol of what we can do when we look up instead of down, when we choose wonder over fear, when we believe that even a small voice sent into the vastness can matter. Because Voyager isn't just carrying instruments and data, it's carrying us, our languages, our music, our laughter, our biology, our greetings to the stars. It carries the sound of a baby crying, a heartbeat, a kiss, and the words, "We are trying to survive our time so we may live into yours." It's hard to think of another object that captures so much meaning with so little technology. And yet, that's the irony. In an age of rapid innovation, disposable electronics, and planned obsolescence, Voyager endures. Not because it was advanced, but because it was built with care, with purpose, with the audacity to try something that had never been done before. It became the longest mission in history, the farthest reach of human hands, a drifting monument to our curiosity. And someday, long after we're gone, long after Earth itself has changed, Voyager may still be out there, moving, waiting, a message in a bottle, written in the language of science, sealed by ambition, and launched into eternity. Somewhere out there, in the cold silence between the stars, a tiny machine is still moving. It doesn't know where it's going. It doesn't know who we are anymore, but it remembers its mission. It remembers that someone once pointed it toward the unknown and said, "Go." Voyager 1 is more than a spacecraft. It's our echo in the universe, our proof that we dared to leave home, that we reached farther than our fears and left behind more than just footprints. We left a voice, and maybe, one day, that voice will be heard. But Voyager's story isn't the end, because beyond every signal we send, beyond every silence we break, there's something even stranger, something waiting in the dark. And if you're ready for that, I'll see you in the next transmission.